All right, 17.2, we're going to deal with a topic that you worked on last year and that you did in the lab last year. So this should be mostly review. We're not even really going to spend much time going over the calculations. We will review a titration calculation in class, but we're going to focus on the titration more from a standpoint of equilibrium than calculating the pH like we did last year. So remember, titration, we're taking a known concentration of an acid or base and slowly adding it to a solution of acid or base to figure out the concentration of kind of our unknown. So when we use titration, you're going to use a pH meter or an indicator to show you when the equivalence point at which the stoichiometric amount of acid and base equals one another. Now when you use your pH meter, it's pretty simple to do that because you're going to be able to figure out the exact pH. If you use an indicator, typically you're going to have a color change. So remember last year when you did titrations, your indicator of choice was phenolphthalein, which went from clear to pink. Additionally, sometimes we use bromothymol blue, which went from yellow to blue, and it was cotton green in the middle. So if we look at a titration of a strong acid and a strong base, what we have here is we have all acid. Then we start adding some base. And what happens is we're going to have to add quite a bit of base initially. But what's going to happen is that change is going to happen very quickly, and our pH is going to happen, or our pH spike is going to happen very quickly when we do this. So if we look at the chart, we reach our equivalence point. And our equivalence point is when our moles of acid equal our moles of base, and the solution contains only water and salt. Remember, anytime you mix an acid and a base in a perfect ratio, your two products are water and salt, and your pH will be 7. So at your equivalence point, your pH is 7. As more base is added, your pH level will increase and then gently level off. So that's a strong acid, strong base, which is the most titration problems that we did last year. How about if you take a weak acid with a strong base? The equivalence point is greater than 7. Now, why is the equivalence point going to be greater than 7? Because your base, you have a strong base and a weak acid. So your equivalence point is going to be greater than 7. When we have a weak acid and a strong base, phenolphthalein is going to be your indicator, simply because phenolphthalein changes colors in that 8, 9, 10 pH range. If your equivalence point is going to be greater than 7, you're going to want your indicator to change colors at greater than 7. So what we've done before is we've had to do the stoichiometry calculation with the weak acid to the strong base, figuring out moles and liters using molarity. And then you're going to have to use your equilibrium calculation to help figure out pH. And we will do an example of this in the 16.2 worksheet. Now, if we look at the process in which this takes, we have an acid with a weak acid and a strong base. What we're doing here is you can see kind of what happens to the equivalence point and how the graph will look based on our Ka values. So as the Ka values get weaker, our pH kind of graph changes dramatically. So if we start off with a strong acid, like in the Ka to the 0, you can see we have a sharp spike and then a change. And our pH, our equivalence point, is going to be around 7. As the acids get weaker, you can see that the equivalence point slowly slides up from 7 to 8 to 9. All right. You could probably say with an acid with a Ka of 10 to the negative 8, your equivalence point is a pH around 10. So just kind of showing what can happen when you titrate a weak acid with a strong base. Likewise, we can do it oppositely. We can have a weak base with a strong acid. Since you're dealing with a weak base and a strong acid, your equivalence point is going to be less than 7. So you're going to want an indicator that changes colors before 7 in that pH 4, 5, 6 range. An indicator that does that is methyl red. You guys have not worked with methyl red simply because when we have titrated in the past, we've done a strong acid and a strong base, or we've taken a weak acid with a strong base. We have not titrated with a strong acid and a weak base. Last thing that's important to note, that you have when you are dealing with a polyprotic acid, you're going to have an equivalence point for each ion or for each dissociation. So what that means is if you have an acid like phosphoric acid, like we have here in the example, you have H3PO3. All right. What's going to happen is you're going to have an equivalence point for each time an H is dissociated. So you're going to have two dissociation curves, one when it loses its first H, one when it loses its second H. So very important to note when you're titrating polyprotic acids, you're going to have multiple equivalence points. So something to keep in mind there, particularly when you have an acid that has 3 hydrogens to give up, as the case with phosphoric. Not so much with 2, you'll see this a lot more generally with 3. So just a reminder, when you're titrating polyprotic, you're going to have multiple equivalence points. So nothing new there. We're going, like I mentioned before, we are going to do a titration calculation in class on the worksheet in 17.2 worksheet. So this concludes section 17.2.